This video is about set operations, that is, ways in which we can take two sets, A and B, and combine them to make a third set. So the first set operation we're interested in is the union. The union of two sets, A and B, is the set which contains all the elements of B and also all the elements of A. So we write it like this with a symbol that looks a bit like a U. The next operation we're interested in is the intersection of two sets. The intersection of two sets A and B is the set consisting of all the things which are both in A and in B at the same time. And we write it like this with a symbol which looks a bit like an N. The next operation is the set difference, and the set difference of A and B, which we write like this with a backslash, and which we sometimes pronounce as A take B, is the set of elements which are in A but which are not in B. And finally, if we have a set A which is a subset of some large set omega, then the complement of A in omega, which we write as A with a superscript C, means the set of all the things in omega which are not in A. So if you like, you can think of this as A complement being simply omega take A, the set difference of omega and A. Alright, so it helps to look at some examples just to get a feeling for what's going on here. So let's fix as our sets. A will be the set 0, 1, 2. B will be the set 1, 2, 3. And C will be the set just containing 4. Okay, if we take the union, A union B, remember this is supposed to be the set of all things which are either in A or in B, or both. So that will be, in this case, 0, 1, 2, and 3. Those are the elements which either belong to A or to B or to both. On the other hand, the intersection, A intersect B, well, this is the set of things which belong both to A and to B. So the things which are in A and in B are just 1 and 2. Okay, next let's take A intersect C. Well, this time, if we look at A and B, they don't have any elements in common at all. So A intersect C is in fact the empty set, because there are no elements which are both in A and in C. Okay, next the set difference. If we do A take B, that means all the things which are in A but which are not in B. So the only thing which is in A but not in B is the element 0, so this is A take B. But on the other hand, if we work out A take C, well, the elements of A which are not in C are 0, 1, and 2. In other words, this is all of A again. Alright, and lastly, let's have a complement. So if we have a set omega being the natural numbers n, so this means the set consisting of 0, 1, 2, and so on, all the non-negative whole numbers, well then the complement of A in omega, which we write as AC, that's all the elements of omega which are not in n. So that will be 4, 5, 6, and so on. Okay. So there are some standard ways to draw pictures of these set operations, which you can see on the right of the page here, called Venn diagrams. So when you make a Venn diagram, you draw a circle or a blob for each set, and you colour in the area which corresponds to the set that you want to illustrate. So for example, this diagram at the top here, this is the Venn diagram for well, which set operation do you think? Pause the video. hope you did pause it. This is the Venn diagram for A, take B. The set difference of A and B. You can see that the shaded area there is the area of the set A, which is not part of the set B as well. So that is the set difference, A take B. Whereas here in the second diagram here, this is the Venn diagram for A intersect B. So sometimes people will say meet instead of intersect. So if you catch me saying A meet B, then what I mean is the intersection of A and B. Okay, next slide. We're now going to talk about the size or the cardinality of a set, which has a nice simple definition. The size or the cardinality of a set X, which we write like this with a straight line on either side. It's the number of distinct elements which are in the set. So for example, if we take the cardinality, the size of the set 1, 2, like this, this set has size 2. And if we take the empty set, the cardinality of the empty set, that is 0. It doesn't have any elements, so that it has 0 distinct elements. And lastly, let's just pay careful attention to what this definition says. You have to take mathematical definitions very literally, very carefully. If I have the set 1, 2, 3, 1, the size of this set is, well, what do you think? Size of this set is 3, right? The number of distinct elements is 3, because the only distinct elements are 1 and 2 and 3. So this last element, 1, is actually the same as the first element. Okay, that's it. That's the size of a set. So there is one special piece of terminology we use about sets. A set is finite if it has size 0 or 1 or 2 and so on, any counting number. Otherwise, if it doesn't have size 0 or 1 or 2 or any other counting number, then it's called infinite. Okay, that's all we're going to do on the sizes of sets.